Here we're going to do a few examples using the limit comparison test. So as a first example, consider the following infinite series. The series from n equals 1 to infinity of 2n squared plus 3n all over the square root of 5 plus n to the fifth. And again, when looking at this infinite series, we would ask ourselves the same questions. What if we just use a test for divergence? Is this a geometric series? Would this be easy to do with integral test? Well, to save you that bit of information, we're going to jump into limit comparison test. It's going to pass the test for divergence. It's not a geometric series. Just looking at this integrand, or the integrand version of this function, is going to be scary if we try to integrate it. And let's just practice the limit comparison test in this case. So again, the first thing we need to do is find comparison series. And we do that the same way we've been doing. We start off with, okay, what series am I given? It's 2n squared plus 3 to the n all over the square root of 5 plus n to the fifth. We ask ourselves, for very, very large values of n, what does this look like? For very, very large values of n. So in the numerator, what's the main contribution? Is it going to be the 2n squared, or is it going to be the 3n term? Well, as n gets very, very large, that 2n squared is going to win. So in the numerator, this is looking like 2n squared for large values of n. Well, in that denominator, we have that square root basically enclosing everything else. So that square root is going to sit there. But we can ask ourselves, well, which character or which term in that square root is actually going to be giving us the greatest contribution? So we have this battle between 5 and n to the fifth power. For very large values of n, the n to the fifth power, that is going to win out. So under that square root, we then have this n to the fifth. So we can rewrite this using algebra as 2n squared all over n to the 5/2 power, which we can use a bit more algebra to rewrite as 2 over n to the 1/2. So this looks like our series function going forward that we're going to compare to. So let's then ask ourselves, what does this series do? Again, what does the comparison series do? In this case, if we look at it from n equals 1 to infinity, the series we have is 2 over n to the 1/2, which, if we want, we could pull that 2 out in front of that series. So we just have the series now from n equals 1 to infinity of 1 over n to the 1/2. And you may have guessed it already. This is a p series. P is equal to 1/2. And since p is equal to 1/2, we know that it is less than or equal to 1. So this series is divergent. Okay, so at this point, we have our original ugly series. We found a series to compare to, 2 over n to the 1/2. We found that that series actually is divergent. And at this point, we're going to jump right into limit comparison test. So the subtle thing we're doing here, we're not even trying the inequality-based comparison test. We're going to jump straight into this limit version. So let's go ahead and do that next. So to do this, we take the limit as n goes to infinity of the ratio of our series functions, which in this case we could write as 2n squared plus 3n all over that ugly square root, 5 plus n to the fifth, all divided by the second series, which in this case is 2 over n to the 1/2. So let's rewrite this again. Since we have the quotient of two fractions, we take the denominator, reciprocate it, and multiply, and we get this is now the limit as n goes to infinity of 2n squared plus 3n all over the square root of 5 plus n to the 5th times n to the 1/2 all over 2. Let's continue this on the next page. Okay, there's no next page. Let's just delete this page. Sorry, we are going to go upwards. Hopefully this doesn't confuse you, to continue on with this limit. So, just doing out a bit of algebra. This is now the limit as n goes to infinity. We can multiply that numerator, or the product of the numerators together. So this is now 2n to the 5 over 2 plus 3n to the 3/2. And that's all over 2 times the square root of 5 plus n to the 5th. And this doesn't look any better. But what we can actually do at this point is try to pull out the largest power of n from the numerator and the largest n power from the denominator. So what this looks like is we can take n going to infinity. We can pull out the n to the 5/2 from the numerator. And it's multiplying then 2 times 1 plus a 3. What's going to be left over is an n to the -1 power. And if we do something similar in the denominator, we're going to pull out the n to the 5th out of that square root. So we're going to pull out an n to the 5 over 2 out of that square root. We still have that coefficient of 2 before that square root, but inside that square root now we're going to have 5 over n to the 5/2, or n to the 5th, excuse me, plus a 1. So we see that this n to the 5/2 in the numerator and denominator, those are going to cancel. And if we rewrite the limit to see what we have left over, this is now the limit as n goes to infinity of 2 plus 3 over n in the numerator, all over 2 times the square root of 5 all over n to the 5th plus 1. So as n goes to infinity, let's see what happens to these terms. Well, that 3 over n term as n goes to infinity, that's going to 0. And similarly, this 5 over n to the 5th term is also going to 0 in the denominator. So this limit is looking like we have 2 all over 2 times the square root of 1, or this is just equal to 1. So again, to bring us back, we just took the limit of both series generating functions. This limit came out to a finite, non-zero number. So by limit comparison test, both series do the same thing. So that's where we are with the big picture of this problem. Let's go ahead and just synthesize the result. So I'll get rid of the start of this limit. So number 4, what we found was, since the series we're comparing to, the series from n equals 1 to infinity, of 2 over n, or sorry, 2 over the square root of n, Since this diverges, and by limit comparison test, both series do the same thing, our original series that's a series from n equals 1 to infinity of 2n squared plus 3n all over the square root of 5 plus n to the 5th. This series must also diverge. So again, we showed that the series we're comparing to diverges. We then hit it with the limit comparison test. And by limit comparison test, both series did the same thing because that limit came out to a finite, non-zero number. Then we can automatically say that our series must also be divergent because the series we're comparing to divergent and limit comparison test says both series must do the same thing. Let's do another example using the limit comparison test. Consider the following example. This is the series now from n equals 1 to infinity of e to the 1 over n all over n. And again, since we're handed a series, we would go through our checklist and try the test for divergence, which is taking the limit as n goes to infinity and making sure we get a limit of 0. It's going to pass this. We then ask ourselves, well, is this a geometric series? Because if it is, we could easily ascertain whether or not it's divergent or convergent. It's not a geometric series. So we could ask ourselves, is this something we can easily just integrate and use the integral test? And well, what I'd like to tell you is integral test, that's always going to be our last resort. So right now, let's go ahead and try some comparison tests. In particular, we're going to use the limit comparison test. And right from the get-go, I want to say we're not even going to try to use the inequality-based comparison test. We're just going to jump straight into limit comparison test. If you want, you could also try to do the inequality-based comparison test. But as we saw before, sometimes that inequality-based test will fail. So let's jump into the limit comparison test. So the first thing for limit comparison test, or for comparison test in general, is find series to compare to. In other words, find the comparison series. And the way we've been doing that is we take our original series and ask, for large values of n, what does the series look like? Or in other words, for large values of n, what term is giving the main contribution in the numerator, and which term is giving the main contribution in the denominator? So, in the denominator, hopefully you can see, well, there's one term there. For very large n, well, that n is going to dominate. Let's see what happens about that numerator. Well, again, we're thinking of as being very, very large. If n is very large, this e looks like it's 1 over a very, 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 very large number. In other words, this e, it actually looks like we have something like e to the 0 sitting there in the numerator. Since n is going to infinity, that 1 over n in the exponent is going towards 0. So in the numerator, the largest contribution actually looks like 1. In the denominator, that's going to be our n. So this 1 over n will be the series function for the comparison series. The second step is figure out what that comparison series does. So we have the series from n equals 1 to infinity of 1 over n. And welp, this is our friend, the harmonic series. In the harmonic series, we know diverges. If you didn't remember that this is a harmonic series, this is also an example of a p-series with p equals 1, which is less than or equal to 1, so it's divergent as well. So again, this is the harmonic series, or it's a p-series with p equals 1. But in either case, it is divergent. So we're comparing our original series then to a divergent series. And we're just going to go straight ahead and try limit comparison test on this problem. So again, for limit comparison test, we take the limit as n goes to infinity of the ratio of our series functions. So we take e to the 1 over n, all over n, divide it by the series we're comparing to, which is just 1 over n. So doing a little bit of algebra, since we have the quotient of two fractions, we reciprocate the denominator and multiply. This is actually the series, or this is, sorry, the limit as e to the 1 over n power over n times n over 1. So we can easily see that those n's cancel out. And now we just have the limit as n goes to infinity of e to the 1 over n. And that looks like, well, e to the 0, which in this case is equal to 1. And again, the limit that we just found is finite and non-zero. So by limit comparison test, both series do the same thing. And just to check our logic, what this means is, well, by limit comparison test, we know both series do the same thing. But we know something about one of those series. We know that our series that we're comparing to, we know that series is divergent. So therefore, we know both series must diverge. Let's just quickly synthesize that into number 4. So since the series we're comparing to, the series n equals 1 to infinity, 1 over n, or the harmonic series, diverges, and limit comparison test told us that both series do the same thing, both series must diverge. So our original series, the series from n equals 1 to infinity of e to the 1 over n, all over n, must diverge as well. So again, the series we're comparing to diverges. Limit comparison test told us both series do the same thing. Because we know something about one of those series, that is the series we're comparing to diverges, we automatically can say that our series also diverges. And that's using the limit comparison test in a nutshell. Also, for the record, in this problem, we could have also set up an inequality-based comparison test. So either would have worked, but you can see that we even need to try and attempt an inequality-based comparison test in order to use limit comparison test.